Let me show you how to be a good Bayesian.
This episode is the first of its kind. Welcome to the very first live episode of the Learning Bayesian Statistics podcast, recorded at StanCon on September 10, 2024. Again, I want to thank the whole StanCon committee for their help, trust and support in organizing this event. I surely had a blast and I hope everybody did. In this episode, you will hear not about one, but two Stan core developers, Charles Margossian and Brian Ward. They'll tell us all about Stan's future, as well as give us some practical advice for better statistical modeling. And of course, there is a Q&A session with the audience at the end. This is Learning Bayesian Statistics, episode 118.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. And if today's discussion sparked ideas for your business, well, our team at PyMC Labs can help bring them to life. Check us out at pymc-labs.com.
Hello, my dear Bayesians. Today, I want to welcome a new Patreon in the Learn Bayes Stats family. Thank you so much, Rob Flannery. Your support truly makes this show possible. I can't wait to talk to you in the Slack channel and hope that you will enjoy the exclusive merch coming your way very soon. Before we start, I have great news for you, because if you like live shows, when I have two new live shows of LBS coming up on November 7 and November 8 at PyData New York. So, if you want to be part of the live experience, join the Q&As and connect with the speakers and myself, and also get some pretty cool stickers, well, you can get your ticket already at pydata.org/NYC 2024. I can't wait to see you there. Okay, on to the show now. So, welcome. Thank you so much for being here. You are going to have the immense honor and privilege to be the first ever live audience of the Learning Bayesian Statistics podcast. Thank you. Of course, as usual, a huge thank you to all the organizers of StanCon. Charles, of course, thank you so much. I know you worked a lot. Michael also, who organized all of that. So I think you can give them a big round of applause because it's absolutely... Okay, so let's get started. So for those of you who don't know me, I'm Alex Andorra. I am an open source developer. I'm actually a PyMC core developer. Am I allowed to say those words here? That's fine. Don't want. Yes, and very recently started as the senior applied scientist at the Miami Marlins. So if you're ever in Miami, let me know. And today we are gonna talk, and of course, I am the host and creator of the Learning Bayesian Statistics podcast, which is the best show about Bayesian stats. I think we can say that confidently because it's the only one. So it's not that hard. But today we have amazing guests with us. We're gonna talk about everything Stan. Today is the nerd panel. So anything you wanted to know about Stan, about samplers, about all the technical stuff behind Stan,
Why does it take so long to have inline there, for instance? Stuff like that. You can ask that. That's going to be like the last 10 minutes of the show, I think. But before that, we're going to talk with Brian and Charles.
So, I'm going to be without the mic that gives to the room for the rest of the show, so that you can hear from the guys mainly. So let's start with Brian. So, Brian Ward, you were a Stan core developer, if I understood correctly. Yes. Can you first give you a bit of a background, the origin story of Brian? How did you end up doing what you're doing? Because it seems to me that you're doing a lot of software engineering thing, which is a priori quite far from the Bayesian world. So how did you end up doing what you're doing today?
Yeah, so I majored in computer science, and I sort of came into this from a very software development angle. So I sort of was always interested in how things worked, so I learned to program, and then I was like, well, how do programming languages work? So I learned about compilers, and then I stopped before going any deeper because there are dragons down there. But sort of as part of my studies, I started working on a project with a couple of my professors that was about Stan, and they were mostly interested in Stan because, in their words, it was the probabilistic programming language that had the most thorough, formal documentation of the language and its semantics. They really liked that they could sort of form an abstract model of the Stan language. And so that was my first time ever using a probabilistic programming language. It was really sort of coming in from that angle. And then since 2021, I've been working a lot on the Stan compiler, but then also just on sort of, like you said, general software engineering for the different Python libraries and trying to improve the installation process on systems like Windows and that sort of thing.
Mm-hmm, mm-hmm. Okay. So we'll get back to that because I think there are a lot of interesting threads here. But first, let's switch to Charles. So maybe for the rest of the audience, Charles was already in the podcast. He's got the classic episode. So if you're really interested in Charles' background, you can go and check out his episode. But maybe just for now, if you can quickly tell us who you are, how you ended up doing that.
So I should mention that I am an understudy. There were actually two other Stan developers we were hoping to have on this panel, and because of circumstances, I ended up being here. But I'm in very good company, and I have a lot of thoughts about the future of Stan, which is the topic of this conversation. But essentially, I've been a Stan developer for 8 years now, and I started when I was working in biotech in pharmacometrics, where Stan was up and coming, but it lacked certain features to be used in pharmacometrics modeling, notably, support for ODE systems, features to model clinical trials. So my first project for Stan was developing an extension of Stan called Torsten, but also in the process develop some features that directly appeared in Stan. For example, the matrix exponential, which is used to solve linear ODEs, the algebraic solvers. And then I became a statistician. I pursued a PhD in statistics, and I continued developing certain features for Stan, kind of in that theme of implicit functions. And I think we'll talk a little bit about that. Nowadays, what I am is a research fellow, which is a glorified postdoc, at the Flatiron Institute, where I'm actually a colleague with Brian. And I mostly do research around Bayesian computation, so that includes Markov chain Monte Carlo, variational inference, and thinking about, probabilistic programming languages today, tomorrow, but also maybe in 5 or 10 years, what these might look like.
Mm-hmm, mm-hmm. Yeah, thanks, Charles. Quick legal announcement that I forgot, of course. For the questions, we're going to record your voice. So if you ask a question, you're consenting to being recorded. If you don't want your voice to be recorded, just come ask the question afterwards or find a buddy who is willing to ask the question for you. And that will be all fine. So that's that. Also, write down your questions because we're going to have the Q&A at the end of the episode.
So let's continue, maybe with like, that's for both of you. I'm wondering, before we talk about the future, you guys work with Stan all the time. So you do a lot of things, but what has been your most exciting recent project involving Stan, of course?
I can go first. So this is a bit further ago, but one of the first like real major win for me was adding tuples to the language. So it's a slightly more advanced type than had previously appeared in Stan. It had a lot of implementation difficulty, but it was a really big change to the language in the compiler that finally made it in. But more recently, like working directly on Stan, we've been trying to add features to try to make it easier to do some of the things that are built into Stan, especially related to like the constraints and the transforms directly in Stan. So trying to take some of the magic that's built in out and let you be able to do things yourself that work much closer to that. And that's been interesting to sort of think about how to make Stan a language that is easier to extend for newer people. So like this next release will have functions that make it a little easier to write your own user-defined transforms that like do the right thing during optimization, for example.
Okay. Oh, that's cool. Can you maybe give an example about such a function that people could use in a model?
Sure. So one thing you might want to do is you might want a simplex parameter, but because you have some understanding of the posterior geometry, you want an alternative parameterization. Like you want to use softmax or you want to use some other thing than what's built into Stan. And you can do this right now and it will work almost the same in almost all of the cases. But going forward, we're trying to make it work the same in all of the cases, right? We're trying to sort of cover off those last things. So like in particular, if you're finding like a maximum likelihood estimate, that is done without the Jacobian adjustment for the change of variables there. But for the built-in types in Stan. But right now, there's no way to have that also happen for your custom transforms, but there will be going forward.
Okay. That's really cool. Hans?
So I have to admit that a lot of my recent work has been more Stan adjacent rather than specific contributions to Stan. And so I could talk about that, but maybe one of the features that we are hoping to release soon and that I developed a few years ago, I prototyped a few years ago, was we wanted to build a nested Laplace approximation inside of Stan. And actually, we developed one, and we had a prototype in 2020. So that already goes back, and we published a paper about that. And then another year or two later, when I wrote my PhD thesis, I had a more thorough prototype that I also released. And then we kind of got stuck. And I can talk a little bit about that. But essentially, Steve Bronder, who was supposed to join us today, he had something came up. Hopefully, he'll be there in the next few days. At StanCon, has really been pushing the C++ code and the development, and we have this idea that maybe by the next Stan release, we'll actually have that integrated Laplace approximation, and we'll make it available to the users. And of course, there are a lot of interesting things and moving parts that are happening around these features, both from a technical point of view. So the automatic differentiation that we had to deploy is, I think, very interesting, very challenging. Also, the ways in which, what are the features that we put in our integrated Laplace? So I don't think, it's going to be as performant as the integrated Laplace approximation that's implemented in INLA. And I can discuss a little bit what are some of the features we lacked, but we also, focused on what are some unique things that having this integrated Laplace approximation in Stan can give to the users in terms of modeling capabilities. And those are things I'm excited about. And there are going to be a few challenges about using this approximate algorithms, just as they are whenever you use an approximate algorithm, and that's going to motivate, new elements of a Bayesian workflow, new diagnostics, new checks that will have to be semi-automated, that will have to be very well documented, and that will also need to be demonstrated, right? These are all the pieces you need for users to use an algorithm effectively, right? And that's part of the journey between we have a prototype, we can publish this in a, what's considered a top machine learning conference. The paper appeared in NeurIPS versus, I kind of want to say we have something that's Stan worthy, right? And the requirements are a little bit orthogonal, right? So it's not like, Stan, one is superior, but there's a lot of extra work that needs to happen, and that will continue to happen, because one of the, I think, open question is, when we make a new feature available, how much responsibility do we take, and how much responsibility do we give to the users? So maybe those are some of the topics that we can dive into. But one thing that I'll say is the tuples that Brian mentioned, that was one of the key technical components that we needed to develop in order to have an interface that's user-friendly enough to use this integrated Laplace.
Yeah, I love that, because I don't know for you folks, but me, if I hear, oh yeah, we integrated tuples, I don't think, it's like that important. But then when you talk to the guys who actually code the stuff and implement that, it's a building block that then unlocks a ton of incredible features and new stuff for users. So,
and we can make that very, very concrete.
For sure.
Actually, to give an example. So, well, Brian, how would you define a tuple?
So in no, I'm joking. So a tuple is essentially just a grouping of different types of things. So the simplest one to think of is like a point in R2, right? Like a XY coordinate is just a tuple of a real number and another real number. But the nice thing about tuples as compared to like an array is that those don't have to be the same type. So for example, in more recent versions of Stan, there is a function called eigendecompose, which gives you a matrix of the eigenvectors and a vector of the eigenvalues both back to you at the same time. And so this actually cuts the amount of computation that has to be done in half, because in previous versions you had to call the eigenvectors function and the eigenvalues function separately, and they were repeating some work, and now it can just give you this object that has both at once. And so that's like one of the really useful things of tuples, is it lets you have a principled way to talk about a combination of different types like that.
Yeah. And so one place where having this grouping of different types is very useful is in functionals, right? So what's an example of a functional? The ODE solver in Stan, it's a functional. One of its argument is a function, right? So the function that defines the right-hand side of your differential equation, and then you need to pass arguments to that function. And of course, the user is specifying the function, and so they're going to specify what are the arguments that we pass to that function. There was this time where this function needed to have a strict signature, right? So we told the user, you're first going to pass, the time, the state, then the parameters, then the real integers, and then the real data and the integer data, right? And you have this strict format, and so basically those are just way of taking the arguments, packing them into a specific structure, and then inside the ODE you unpack them. And so not only was this tedious, it's actually it can lead you to make your code less efficient if you're not being careful about distinguishing the what's a parameter and what's a data point. And one experience of that I had collaborating with applied people, with epidemiologists, so with Julien Rioux. This was during the pandemic, during the COVID-19. At some point, Julien reached out to the Stan development team, And he said, he's developing this really cool model, but right now it takes 2-3 days to fit, right? Something like that. And we're not at the level of complexity that we want to be at, right? And so I have to give really most of the credit to Ben Bales, who was also a Stan developer at the time. And, we took a look at how the ODE was implemented and how it was coded up and how the different types were being handled. And we realized that way more of the arguments that were being passed were parameters than was necessary. And once you correct for that, the running time of the model went from 2-3 days to 2 hours. Right? So not only is that much faster, and that's good in terms of reproducibility, that also means you can then, keep developing the model and go to something more complicated, right? So having this kind of tuples, well, really what it gave us was variational, what's called variadic arguments, where that was a big step, actually, where now, you don't have those strict signatures when you pass the functionals. People can really pass different things. Now, for the integrated Laplace, so I realized we haven't really defined what it is. But basically, what I'll say is that there are two functionals that you need to pass, right? One is you're defining a likelihood function, and the other one is you're defining a covariance function. And so we want the users to be able to use variadic arguments for both those functions that they're defining. So they're not, construed by types. That way it's not tedious, it's not error prone, or it's not prone to inefficiencies, right? And that's why those tuples, to make the code user-friendly, to probably decrease the compute time that users will spend on this algorithm. That's why that kind of stuff is important. The power users, they don't need it. They can handle the strict signatures. I handle the strict signatures, right? No problem. But once you start using other probabilistic programming languages, you realize that one of the big strengths of Stan is the attention it gives to users, to API, how mindful it is from the users. Other languages, you can tell that it really feels like sometimes they're written for software engineers, and the software engineers are the ones who are going to be the best ones at using those languages, right? But I think that that's one of the strengths of Stan, and that some of the innovations, are maybe going to be less technical or algorithmic, although those exist, and maybe we'll have time to talk about it. But actually, making this more user-friendly, less error-prone, less inefficiency-prone.
Yeah, and that definitely comes up, and I think it will come up whenever we're working on new features for Stan. There's always sort of two users we have in our head. There's the user who is already at the limit of what Stan can do and wants to fit the next biggest model, and how can we help that user, but also the user of they have a relatively small model that they just can't figure out right now, and can we make that user's life easier too? And sometimes they're actually sort of fighting each other, but usually we can find features that actually make both of their lives better, which is the ideal circumstance.
But by the way, kind of in the spirit of that, apparently most of our Stan users are BRMS users, right? I think that's established, right? And a BRMS really gives you this beautiful syntax that people can play with, that people can reason with. Personally, I like the Stan language. That syntax is a bit more explicit. But even that syntax in the Stan model is a simplification of, what Stan is doing under the hood, right? I'll give you a simple example. Those tilde statements that you have in the model block, right? That's because people like Andrew Gellman like reasoning about models in a data generative fashion, right? But really, what's going on under the hood is we're incrementing a log probability density, right? So different users function with different level of abstractions, depending on whether they're statisticians or, more software engineering, maybe ML-oriented people, or maybe scientists who primarily reason about covariates, right? That's where I see one of the big roles that BRMS is playing. And we need a way that's maintainable, that's, avoid compromises, to kind of like cater to these different users. And in fact, we should talk about BridgeStan and a new community of users we're hoping to reach with Stan, maybe at some point.
Yeah, I'll add that to the notes.
Good.
Yeah, so many questions. Thank you so much, guys. I think, something I'd like to pick up. We'll get back to INLA also at some point. I think it's going to be like the how do you say fil rouge in English? The thread. Thank you. The red thread, you can say that. I don't know. So it's going to be the thread. But first, talking a bit more about the beginners you were talking about and the user who is trying to get his model work but cannot figure it out yet. Do you see a common difficulty that these kind of users are having lately, maybe in the Stan forums, things like that, and maybe you can tell them how to use that right now, or maybe tell us what you guys are doing in the coming months to address that kind of obstacles?
I think there are two, and they're sort of different. So I think a lot of users who are coming from more traditional like R or Python and are trying to write Stan themselves for the first time, the difficulty of just having a compiled language at all, both in terms of the extra installation steps, but then also like dealing with static typing, and if you're not used to sort of thinking about variables in this way. And so there are things we've talked about of trying to work on that, but a lot of what like I've invested in is just trying to improve like the error messages the compiler gives you and trying to have them less be like what a compiler engineer knows went wrong and make it more like what you think went wrong.
Yeah.
But I think the second class that I see, and this is sort of going back to Charles's point, is I think we have a lot of users who will use a tool like BRMS or RStan ARM, and it will get them as far as it gets them, and then they want to go a bit further. But I think the issue is if they've never written any Stan code at that point, they ask BRMS, hey, can you give me your Stan code? And they're given this model that like would have taken them several months to write themselves, and now they have no hope. Like it's sort of, they're starting off in the deep end already because they already have a very powerful model that they just want to tune one bit further. And that's like a much harder thing, both like in terms of software, but also like pedagogically. I don't know how to handle that. I don't know if you have more.
I think a bit less about beginners. Okay. So let me nuance that a little bit. So I teach workshops. I've had opportunities to teach, and actually, I think about some fundamental questions that a beginner is likely to ask, but for which we don't have great answers to. And I'll give you one example. For how many iterations should we run Markov chain Monte Carlo? Right? That's an elementary question, and it's actually not an easy one to answer, especially if you start digging and thinking about, what is the optimal length of a Markov chain? What is the optimal length of a warm-up phase, of a sampling phase? What is the number of Markov chains that I should run given, some compute, that's available to me? And then you get into a more fundamental question, which is, what is the precision that people need from their Monte Carlo estimators? Right? So I asked to, an audience of scientists, what effective sample size do you need? Right? What summaries of the posterior distribution do you need? Are you really interested in the expectation value, or do you need the variance, or maybe you need these quantiles or these other quantiles, right? And we have some unfortunate terminology, like, people say we're computing the posterior. That doesn't mean much. It conveys a good first-order intuition, but not a good second-order intuition, right? I like to say we're probing the posterior. And then we need to think about what are the properties of the posterior that we're actually pursuing. And so then we get into, people ask me, when should I use MCMC or variational inference, right? So, people criticize variational inference. They say, well, even when you solve so what does VI do? Maybe just as a summary is, you have a family of approximation, right? For example, Gaussians, right? And then within that family of approximation, it tries to find the best approximation to your posterior. And people will dismiss it because they say, look, even if you solve the optimization problem, at the end of the day, your posterior is not a Gaussian, so your optimal solution is not good. It has what's called, what people call an asymptotic bias. Whereas MCMC, that with enough compute power, and enough can be a lot, right? Eventually you'll hit arbitrary precision, right? But now if I think about, I'm trying to probe the posterior, well, maybe that Gaussian approximation does match the expectation value, does match the summary quantities that I'm interested in. Maybe, it captures the variance, or maybe it captures the entropy, right? So maybe, maybe that is the pedagogical work that I'm trying to do for beginners, with the caveat that I don't have great answers to all those questions. I think these are real research topics. But if I think about, one goal, for example, that I would like to achieve, I would like to, I want it to be part of the workflow, and people are doing work on that. Aki Vettari is doing great work on that, to only name one person. If once people figure out this is how precise my Monte Carlo estimators need to be, I want that to be the input to Stan. And then I want it to run the Markov chains for the right number of iterations in a way that gives you that precision without wasting too much computational power. And we're not there yet. We have promising directions to do that, which also come with, their fair share of challenges. But yeah, that's the kind of thing I want to do for beginners and for intermediates and for advanced and for myself. But yeah, the beginners ask the right questions and the difficult questions.
Okay, thanks, Charles. Nice save. No, so more seriously, so yeah, Brian, I was wondering, so if you had, let's say Stan Ulam, right? He comes to you in a dream, and he's like, okay, Brian, you've got one wish to make Stan better for everybody, okay, including the beginners, Charles. And so what would it be?
This is like a genie powerful wish, right? I can rewrite the history of the, okay. Yeah. Something that we've talked about again and again, but it would just be such a huge lift. But if I'm allowed to go back to the start, I think that there's been a lot of talk about how the block structure of Stan gives a lot of power, but it also makes a lot of things limiting. It's right now, if you want to do a prior predictive check, you oftentimes need a separate model that looks a little different than the model you're actually writing. And this is one of the things that's great about BRMS, right? Is the single formula can be turned into all these models at once. But there has been previous research. So Maria Goranova, she did a master's thesis and a PhD thesis on a tool she called SlickStan, which was a Stan with no blocks. And so it sort of would you would write your Stan model as you do now, but without saying what's data and what's parameters, and then you would just give it data, and it would then figure out, okay, these are the data, these are the parameters, here are things I can move to generated quantities, and it would sort of be a much more powerful form of the compiler that would really capture a lot of these ideas, but it would also be sort of a fundamentally different thing than Stan, and so if I could really do anything in the world, that would probably be it, but I don't know if that will ever make it there, that there's a lot of existing stuff that we would have to give up, I think.
Yeah, okay, yeah, but I understand. And if you're interested, Maria Gorinova was in the podcast, so yeah, you can go on the website, learnbasedstats.com, and there is a small stuff on the right, on the top, you can look for any guest. So Maria Gorinova, that was a great episode because I think she's also working on automatic reparameterization, if I remember correctly. So if you ever had to reparameterize a model, that can be quite frustrating if you're a beginner because you're like, but it's the same model. Yeah. I'm just doing that for the sampler. And so that's one of the goals of that is just having the sampler figure that out by itself.
Yeah, and then she also did some interesting work on automatic marginalization where it's tractable, which was very cool because that's another I don't feel confident in my own ability to marginalize a model off the top of my head, so it's like I know that's a thing that new users hit a lot.
Yeah. I mean, you hit that quite a lot, and yeah, if we could automate that at some point, that'd be absolutely fantastic. Yeah. Charles, I think we've got 9 minutes before the Q&As. So I'm going to give you a choice. No, so we could go back to talk about INLA a bit, because I realize we should have done something at the beginning, which is defining INLA and telling people why that would be useful and when. We can also talk about BridgeStan, but I think, Brian, you can talk about BridgeStan too, so your call, Charles.
Let's talk about BridgeStan, right? Or let's talk about BridgeStan.
Let's see how fast I can do it. Maybe we can do both.
Yes and yes.
Yes. So Simon's talk earlier mentioned BridgeStan, and if people aren't familiar, this was something that Edward Raldis, who's a Stan developer, started a few years ago when he was visiting us in New York, and it drives me crazy that I didn't think of this. Like Edward deserves so much credit because it was sitting there like all this time. But what it essentially does is it, through a lot of technical mumbo jumbo that you should ask me about later, it makes it very easy for people to use Stan models outside of Stan's C++ ecosystem. And so if you have a model in Stan, but you want to use an algorithm that's only implemented in an R package or that you're developing yourself, it really lets you get the log densities and the gradients with all of the speed and quality of the Stan math library. But you can use these Python libraries or these like experimental things that you're working on. And so it's we have a paper and it has a few citations already of people who have been using it to develop new algorithms. And I know a lot of work that Bob has been doing recently has been using it. And so that's one way where, especially one of the things we're thinking of for those users who want to push the edge is new forms of variational inference and new forms of HMC. And it has already been like a really huge boon for that research. And
at the Flatiron Institute, we do a lot of algorithmic work on new samplers and new variational inference. And we now use BridgeStan all the time. I'll give you two good reasons, and there are probably more, but one of them is that gives us access to Stan's automatic differentiation. And if you look at a lot of papers that evaluate the performance of algorithms, they do it not against time, but against number of gradient evaluations, because that tends to be the dominant operation computationally. And so now you write your sampler in Python, or maybe in R, or you write your VI in Python and R, but you still get the high performance from using Stan, right? So that's great. And then the second thing is that means that you can now test those new algorithms that you've developed in a pretty straightforward way on Stan models and a library of Stan models, including PosterioDB or maybe some other models that you've been using, and those models are very readable. It standardizes a little bit the testing framework.
Yeah, and so it has changed my thinking a little bit as someone who works a lot on the Stan compiler, of thinking of Stan not just as its own sort of ecosystem, but also as like a language for communicating models. Like I find it really helpful. Someone can describe a model in LaTeX up on a slide, but as soon as they show me the Stan code, I'm like, oh, I get it. And even if my job now was to go implement it in PyMC or something, I think it still helped having this language that sort of is a little bit bigger than itself, or a little bit bigger than it used to be. We're now I see Adrian here is in the audience, and he has an implementation of HMC in Rust, but you can use Stan models with it because of BridgeStan, and it sort of has opened up Adrian's in the back. But it's opened up sort of the world of things that Stan can be, which is one thing that I think is very cool.
Yeah, and I think so. When I spoke about the new community of users that I think we're going to reach, is there are people who write their own samplers who have particularly difficult problems, and even today we've had two examples, at least two examples, of people who departed from, the traditional samplers that are implemented in STAN, either, to implement tempering or to, implement massive parallelization. And so, I really think that, there is a group of people who, for their problems, like to develop and try out certain samplers. And, that's also going to drive research for what could be the next default sampler or variational inference or approximation in STAN. They are candidates for that. Although it's true that, the more we learn, the more we develop new samplers, the more we realize how good nuts is. Right? But things are going to change over the years.
Okay, awesome. Thanks a lot, guys. So I still have a ton of questions, but already let's open it up to the audience. Are there already any questions, or should I ask one? Okay, perfect. So, mentioning the new samplers that you guys are developing at the Flatiron, and also I have a lot of guests who come on the show and talk about new samplers, normalizing flows, for instance. Marie-Lou Gabriel was on the show, also Marvin Schmidt. I know Paul Birkner is here. He works a lot on base flow with Marvin Schmidt. And they are doing amortized Bayesian inference. So I'm really curious how you guys think about that and STAN, basically, because most of the time it's also tied to increasing data sizes, and so people are looking into new samplers which can adapt to their use case better. So I'm curious how you guys think about that in the STAN team and what you're thinking of developing in the coming month about that.
Yeah, I think one of the challenges that these approaches often one of the motivating reasons for them is that you can get a wall clock time reduction by just throwing a massive amount of compute at it with GPUs, which is one place where Stan's GPU support is still kind of piecemeal, like we're working on it, but it's sort of like we can't compete with Google developing JAX, Yeah. And so Simon's presentation earlier showed that on CPU, Stan actually beats JAX, or BridgeStan, can be faster than JAX. But on GPU, we have sort of no hope, and I think that or at least at the moment, no hope. But I think that's where these approaches become really challenging, is trying to think of, and I think it's sort of an almost existential question of is Stan just the CPU solution, right? And is something else better? Because there are things about Stan's sort of core design that don't like GPUs. It's a very expressive language, and GPUs really like less expressive languages that are much more easier to guess what you're going to do next. Mm-hmm. And so I think that is something that, I personally believe there will always be sort of a community of researchers working on their laptop or that sort of thing. And so I think that there will always be a place for these CPU bound implementations. But yeah, if you can predict that, you can probably make a lot of money. So,
Charles?
Yeah, I'm going to try and return to the original question, which is, so there are a lot of algorithms that are being developed, and there are a lot of good ideas that go into developing these algorithms, and there's some good experiments and some good empirical evidence that supports why you might want to use those algorithms. Nonetheless, 80 to 90% of the time, when I read a paper about a new algorithm, it doesn't give me enough information as to whether I should now start using this algorithm to solve my problem. And there is so what does that mean? That means that usually you need to somehow, implement that algorithm and test it yourself on your own problem. And that's fine. But I think that a lot of these algorithms out there are not yet battle tested. And, we're kind of in a situation where okay, we maybe we like the prototype and maybe it's promising. Do we put in the developer time to build this in Stan? And it's a bit of a cycle, because once it appears in Stan, then it really gets battle tested, and then we get feedback from the community, and we can try to learn things about this algorithm. We can try to improve it. That's actually what happened to the no U-turn sampler, which has evolved since its original inception, right? So I'm of the opinion that my bar for scientific papers is, it presents a good idea and it's thought stimulating. But I don't think it tells me this is the next thing we should build in Stan, right? I think BridgeStan can alleviate some of that, because, it makes it easier for people to build implementations that can then be tested in Stan. And then, we kind of get into battle testing things. Maybe someone builds a Python package that is compatible with BridgeStan, and maybe the process becomes, instead of the Stan developers, the Stan community brutally evaluating an algorithm before deciding to put some amount of work, maybe first this package gets used, and it's developed by an algorithm developers. But this is the broader question of, how do algorithms get developed, implemented, and adopted? And I'll tell you what, another big criterion here is the simplicity of the algorithm. That it plays a huge role into whether an algorithm is adopted by developers, by users, or not, right? So the answer is I don't know.
Yeah, that's always a fun answer. Any questions?
I'm going to bring one up for my neighbor.
Wait. Perfect. We needed the mic.
So what do we do about algorithms that are good for specific situations but not good for other things? Like, so far we've only developed like black box algorithms that we kind of hope work everywhere. We don't have any kind of real specific algorithms for anything. Is there any future for that?
I mean, this is, I think this is one advantage. So I'm going to quote the person who just asked the question, but like one thing Bob has said a lot is like, the reason we don't want to just put 30 samplers into Stan is then a lot of practitioners would try all 30 of them and then just report them. Like, it just, like, there's an advantage of sort of being a great filter and like being very conservative in what is actually in Stan. But I do think this is one advantage to making it easier to broaden the ecosystem, where like now I think a future for that kind of algorithm is in a R package or a Python package that can interface with, there are now sort of existing examples out there of like an implementation of an algorithm that has support for Stan models and PyMC models. So it can kind of bridge gaps between communities, but also sort of by, if you have to install a separate package, that makes it fairly clear that this is like for a separate purpose. And so I think that's what I would say the future is for those.
Yeah, I agree.
Do you have an intuition how easy it is for the Stan compiler to figure out whether a model is generative and then to be able to like sample from it? I mean, of course we can do it in generative quantities, but it's always awkward to double code our models.
This is a question that also sort of does expose a bit of my sort of not traditional statistics background, is that I have never been presented with a definition of like generative or graphical model that is precise enough for me to actually answer this question. I think that there are definitely easy cases and hard cases. I suspect that in general it would be impossible, but it's also, I think it's probably likely that we could have a system where like it tries really hard and then if it doesn't succeed in a minute it gives up or something like that. Like there are all these sorts of tricks in the sort of compiler world, but I think that this is another one of these things, kind of like GPU support, that because you can write basically anything you want, you can also write sort of the worst possible case for this kind of automated analysis. But An open question I've had for a long time is like, what percentage of Stan models in the wild are generative or not? Like, if that number just naturally is 80, 90%, I think then this is like a very fruitful thing. But if it's like, 60, I don't know, or less, I'm not sure.
More like 80, 90 plus.
That's been what I've heard, is that it is more like, it is fairly high. But yeah, I think it would be something that's worth looking into, but I would need some hand-holding on like the statistic modeling side of that, actually. Oh. Sorry, I shouldn't call on people. But.
Hi, so I have a question about more on the people trying to implement models in Stan. And say there's a model and it's just, it's taking a very long time. And people think, oh, well, Stan, they might have some complaints, or I say it's too slow. But what I found in practice also is I'm never clear sometimes what parts of my model are causing the delay. So what are the slow bits? Or it could either just be like mathematically this is just harder to estimate, or there's some shape of my posterior that's really harder to navigate. But I don't really get that feedback unless I'm like fixing certain parameters, toying with other things. Is there any way to allow, give that feedback of, well, what's causing some issues?
Well, to follow up that question, maybe if you ever thought about modeling that, sorry.
So I remember maybe a year ago, I met Andrew Gelman and Mitzi Morris in Paris at a cafe. We just all so happened to be in Paris. And we started brainstorming. We had an idea of a research project, which is how much can you learn about your model and your sampler by running 20 iterations of HMC? And the idea that fail fast, learn fast, and that the early iterations of a Bayesian workflow should be based on that. And I think that a lot of the statistics literature and the more formal literature, kind of imagines that you've done a really good job fitting your model, you've thrown a lot of computation, or you've waited a long time, and we want to figure out what are the lessons that you can learn quickly, right? So now. I can talk a little bit from experience, and I can give you that. But we kind of want to make that also part of the workflow and the early iterations that we can learn with fast approximation, and then hopefully we'll have a good answer to your question.
There's also a tool for instrumentation.
Yeah, I was going to say, in the immediate sense, there is the ability to profile Stan models. You can write a block that starts with the word profile and then a name, and then you can turn that on when you're running it, and it will give you a printout of like, oh, the block named X took this percentage of the time, the block named Y took that percentage, and it can help you identify at least like, oh, here's the bad line. Now, it might not help you figure out what you need to do instead, but that's where I found that like there are some real wizards who live on the Stan forum, some of whom are in the room, and some of whom are completely anonymous and will never meet them, but they're super helpful. So if it's a model that you can share, that even you can share a snippet of, like there is a lot of human capital. But yeah, automating that and putting that into documentation is an ongoing thing.
Yeah. I mean, plus one to the human capital and the contributions of everyone here who comes to this conference, who teaches tutorials, who demonstrates, their models, who shares the documentation, who makes their code open source. I mean, that's also one of the things that makes a programming language work.
Time for one last question.
So I was thinking, if you go back some decades, 50, 60 years or 48, if you develop a model, then you have to develop a way to sample from the posterior and stuff like that. But maybe fast forward to today, and maybe my advisor could be thinking, when I was a boy, I had to write my own sampler. So now you can have people that can be, designing models or new ways to model, observe data, but they maybe don't have to think too much about that computational side. So what do you think about, the effect of Stan and similar languages on opening up this research in Bayesian modeling to people who maybe are not numerical analysts or stuff like that.
I think you should bring your advisor to StanCon.
Yeah, so one way to think about this question is to think about how old Hamiltonian Monte Carlo is, right? So the original paper is from 1987, and yet it was largely unused by the broader scientific community until Stan came out. And what were the technological developments that enabled, Stan to make Hamiltonian Monte Carlo the workhorse of so many scientists? I mean, that's something worth thinking about. Though I should say the one exception, one person who did use HMC through the 90s and 2000s is Radford Neal, right, who did manage. But otherwise, the tuning parameters, the control parameters, the requirement to calculate gradients, that was an obstacle to many people. And so instead of using HMC, they're using, other samplers, which we know perform between less well and dramatically less well in many cases, right? So I think it's great that we have this, these black box methods. But the one nuance that I will say is that the algorithm is not the only thing that's black boxified in Stan. The diagnostics, the warning messages, the generation of those things, the fact that, these things are generated automatically, that's what makes a black box algorithm reliable.
Yeah.
It was the derivatives, too.
Yeah, the auto-diff.
There wasn't a good auto-diff system when we built Stan.
Yeah. So I mentioned gradients, no?
I'll caveat this a little bit with the previous question hints at the fact that these things are never truly black box, right? Because when you're facing performance difficulties or when you're at the edge, you do need to have a fairly sophisticated understanding of what's happening. Like if you ever have used the reduced sum function in Stan, right, that is technically like an implementation detail that you are having to exploit to get the speed you need. And so there's always a fuzzy boundary here. But I think that like it does help like lower the barrier to entry, even if sort of the hypothetical ceiling can stay as high as your imagination.
Yeah, that's true. We could be more black box. But seriously, huh?
Yeah,
I think that people do tweak and manipulate the methods a lot, and they need to understand some fundamental concepts.
Awesome. Well, I think we're good. Thank you so much, folks, for being part of the first live show. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.